we've been talking about how a system can exchange energy with its surroundings. That can happen by heat, caused by a temperature difference, or by pressure volume work. So the heat is equal to mc delta T, and the work is negative P delta V. And these can be going, you can have work going to the system and heat going to the surroundings, or they can both be going in the same direction. All the combinations are possible. So the change in internal energy, delta E, is the measure of all the energy being exchanged. That's the heat and the work, right? So delta E equals Q plus W. Well, what if there's no change in the volume? We do this in a container with a fixed volume when we don't allow the volume to change. Well, then the work is zero, right? Because work is negative P external times the change in volume. If the change in volume is zero, then the work is zero. And that greatly simplifies things. So, at constant volume, the change in internal energy for the reaction is equal to Q at constant volume, because W was zero. We can't just observe the temperature changes of individual chemicals in a reaction. We can look at the temperature of the reacting solution, perhaps, or if it's a solid, the temperature of that, but after it reacts, everything changes and we can't measure individual temperatures. So what we do is we measure the temperature change in the surroundings. So we control the surroundings, and we use what's called a bomb calorimeter. Unfortunately, nothing explodes here. Bomb calorimeter. So this is an insulated container. So the Q for the system is equal to negative Q for the surroundings. And here we've caused the surroundings essentially to be limited to the calorimeter by insulating it very well. So then we're looking at negative Q cal, the change in heat of the change in heat energy of the calorimeter. So a technique called calorimetry is one where we measure the heat of a reaction by looking at the change in temperature of the surroundings. So we've got the system, this reaction, and we often want to know, well, how much energy does it give off, or how much energy does it absorb? And one way to measure that is to allow it to exchange heat with the surroundings, look at the change in temperature of the surroundings. Q equals mc delta T. We can figure out how much heat was given off or absorbed by the reaction. So this is a diagram of a bomb calorimeter. This is the bomb part. And this is frequently used for measuring combustion reactions. So you've got your little sample in here, and this is full of oxygen, and there's an external electronic ignition, and you can get this to burn in here. But it's all tightly sealed, and so the volume can't change. So no work can be done. Around this bomb, we have water with a stirring mechanism and a thermometer. And then the walls of this outer part are well insulated. So all of the heat that's lost by this reaction is going to go into the surrounding water, and we can measure the change in the temperature. This is assuming that no heat escapes. So Q for the calorimeter is C for the calorimeter times delta T. We're using the calorimeter constant, which is the heat capacity of the calorimeter, because the mass of the calorimeter doesn't change. So you measure the constant for the calorimeter, and then you don't need the M and the CS. So delta E for the reaction is equal to Q for the reaction. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. So there's the information that we were given, and we want delta E for the reaction in kilojoules per mole of hexane. So let's write these numbers down. We have a mass, we have a couple of temperatures. So here we have temperatures. We have an initial and a final temperature, right? Goes from this one to the other one. So we could calculate delta T. Is that the change in temperature of the reaction or of the calorimeter? That's the calorimeter, right? We're doing this in the bomb calorimeter, and the temperature rises from here to here. We can measure the temperature of the calorimeter. We can't measure the temperature of the reaction, right? Because it's just like gases, and it's mixed with oxygen and stuff, and you can't. So that's the change in temperature for the calorimeter. Is this the mass of the calorimeter? No, it's a mass, but that's the mass of hexane, right? And then what's this? So we calculated the moles of the hexane. This is the amount of energy released for this many moles of hexane. So to get kilojoules per mole, I'm just going to take this and divide by the number of moles. So 70.2498 kilojoules. I'm going to divide by and I'll get kilojoules per mole. It's all got very squishy in there. Did I do that right, or did I mess it up again? Wouldn't the sig fig? Yes, it would. Thank you. This one has 3. I was zoomed in. So it's over here, it's over there, and so -10 or negative 3.91 times 10 to the 3 kilojoules per mole. questions? Wasn't that fun? Said no one ever? Got the answer right though. That's always encouraging.